All right, so we're going to look at three different ways things can become charged. So charging by friction. This is what you've probably been exposed to the most in real life. So think of times where you've been shocked, not like sticking a fork in an outlet shocked, but just like oh. Okay, and what caused that to happen? That's what I'm trying to figure out. Okay. Um, Focusing. There it is. There it is. What, like, no, anybody have times where you've like consistently been shocked by stuff? What, when was that? Okay, there's a reason.
Sometimes we go to like a little kid playground full plastic slide.
Yes.
Sometimes I put my hand on it and shock me.
Yes, plastic slides, like playlands, uh, trampolines, petting a pet maybe in the wintertime, uh, putting on certain clothes, like jackets more specifically, getting in and out of a car. Okay, all these are charging by friction. What this means is um, you're taking materials, one material that likes electrons and another material that could be okay with losing electrons. And when those two materials are rubbed together, electrons are being ripped off of both materials. But the one material that likes electrons becomes negatively charged, and the material that is okay losing electrons becomes positively charged. Both these objects are now able to shock something. Okay. Now, the ones that tend to like or okay letting go of electrons are more natural, more organic in nature. Exception would be nylon. And the things that would like electrons, become negatively charged, are more synthetic in nature. Uh, Exception is silicon. But like those two materials, when rubbed, if you take one from here and one from here, rub them together, one's going to become positive, one's going to become negatively charged. Good with that? Okay, so charging by friction. All right, so if you have a metal charged by friction, charge it negatively by friction, how are the electrons arranged on that charged, negatively charged sphere? Will the electrons go through the entire volume of the sphere? Will it go through the entire volume but be more concentrated where it was rubbed? Will it go on the outside equally distributed around? Will it go on the outside but more concentrated where it was rubbed? Will it only be charged where it's rubbed? So this is a factoid, and you're just kind of guessing at this point. And I'm going to tell you the answer. Correct answer for a conductor is C, on the outer surface equally spread out. They're trying to get away from each other as much as possible. Okay, Zach. So your hand like stands up on it. Yep, and we'll get there. We will definitely get there. Yep. Good with that. Versus an insulator, if an insulator is rubbed by friction, charged by friction, it's only going to be charged where it was rubbed. Okay, the other molecules are like, we don't want your electrons. You just keep them to yourself, thank you very much. Okay, and it's only charged where it was rubbed. Versus a conductor, it spreads out evenly. It's like the sea of electrons thing. Good with that? Okay, those are factoids. Important to remember for the lab today. Okay. All right, so that was charging by friction. Charging by conduction is the second of three ways. Okay, charging by conduction. So conduction means contact. So if we have a neutral charged metal slab, it's a neutral conductor, and then we bring a negatively charged object near. Okay, the electrons in the neutral piece of metal polarize. They run away. Like, ah. Okay, leaving this, it's still neutral. It's not been charged yet, but it is polarized. Okay, when this touches that, that enables, that physical contact enables the bridge necessary for electrons to transfer. Okay, fact. Electrons will always go to a better environment. They will never be satisfied, even if they have a 1-to-1 ratio. Okay, if they can go to a better environment, that's where they're going to transfer to. Okay, so if you're an electron, where would you rather be? In this negatively charged object, over here where you see some exposed protons? Protons look way better than a bunch of electrons. And so they're like, boom, we're out. And so they come over here, and this now becomes what charged? Negatively charged. Okay, charging by conduction, contact. Okay, good with that? All right, give this one a shot. Thumbs up when you have a guess. Have a conversation.
Doesn't matter.
Correct answer is? Let's find out. So, inside here, protons stay put. Electrons are doing what? Like, woo, look at all the protons. And so when the positively charged object touches, that enables transfer to go on. And so electrons would rather be in this more target-rich environment of the strip. So it pulls electrons off, leaving the sphere electron deficient. Therefore, it is now positively charged. That makes sense? Okay. So C is correct. Good? All right. Before we talk about the third way of charging, we need to introduce this concept of ground. I'm assuming you've heard of this. Well, many of you, like electrically, not in terms of punishment, but in terms of like, hey, let's that got grounded, or connect this to ground, or this we needed a ground, like have a ground wire, something. Okay, so this actually means, so in residential, in your houses, there's 3 wires connected to outlets. There's a white, a black, and a green. The green is a ground wire, and that is physically connected to your plumbing in your house, the pipes, which goes to the dirt. That's where the term ground comes from. Ground is something huge and neutral. It has this idea that if you took a 5-gallon bucket and you dumped it into the ocean, did you just change the sea level? Well, actually, no, you didn't change the sea level. Okay, like it's okay. So even if you dump a bunch of electrons into the Earth, the Earth is still neutral. Okay, in the lab today, your body is going to be huge and neutral compared to the thing we're going to be working with. Your body would be considered ground compared to what we're working with. Okay, Joey? Yeah, yeah. So like if lightning hits the Earth is still neutral. Okay, so some examples of this you see in life, if people are working with like expensive electronic equipment, they would not want to zap it by accident. So these grounding strips. When trucks are unloading their like stuff, friction can develop, and if this is flammable, that could be fatal. So like gasoline, so they have a grounding strip prevent that. Or if like trucks or wagons are unloading grain at an elevator, that dust is combustible, and so you're going to have a grounding strip to prevent that. The chains on buses that drag are grounding strips. They connect it to the ground, preventing a static discharge if they accidentally are filling it up at the gasoline station. Okay, you can touch your car. I do this all the time, especially in the wintertime. Touch your car before you pump your gas. If there's any discharge, if any shock, you'll take care of that. Chances are very slim, but it's an easy safety. Okay. All right, so that's ground. We're going to incorporate that by charging the third way by induction, not conduction, but induction. Okay. This is a process. It's not as easy as just touching it. I'm going to take you through that. So, first step is we have a neutral conductor, and then we bring a positively charged object in. Okay. Think what happens in that conductor. What happens in response to that? What happens in response to that? Okay, hopefully you said protons stay put, and electrons are like, woo, buddy, look at all those protons over there. Polarizes. Good with that? Okay. Then, thank you. Then, so what we do is we connect it to ground. So electrically, if you've ever seen diagrams with circuits and stuff, you might see this symbol. This means ground. You're connecting it to ground. Okay, so we're connecting it to something huge and neutral. Has a 1-to-1 ratio of protons and electrons. So remember that electrons are always looking for a more target-rich environment. They're never satisfied. 1-to-1 does not necessarily mean they're happy. They're greedy. They're always looking for greener grass. Okay, so if you were an electron, where would you rather be? Up here where there's a bunch of exposed protons, or down here where it's a 1-to-1 ratio? It's like, woo! Look at all those protons. Woo! And so electrons come up from here and they're like, hey, how you doing? Nice, this is good. Okay. So we're not done yet. Then you take away that path to ground. You remove that. Okay. You strand that. Okay. And then we take away the positively charged object. What do you think happens with these electrons now? They're like, oh man, let's go back home. They're like, whoa, where'd you come from? Who invited you? What? And now this is now charged what? Negatively charged. Charging by induction. Okay. Notice we never touched it with a charged object, but we grounded it. Here's the process, if I could summarize. You bring in a charged object causing this to polarize. You taunt it, tease it, okay? Connect it to ground, allowing electrons to transfer. And then you remove that path to ground. And then you remove this, leaving that charged. Charging by induction.
Can you do the same thing with a negatively charged?
Funny you should ask. Have a conversation.
Do the same thing.
So can I use a magnet to like inductively charge?
No.
No.
No. Okay, what do you say? Correct answer is? Show me. A, B, C, D, E. Okay, here we go. So, this is negatively charged. Okay. So, in our neutral conductor, how do these respond? What happens inside there? Electrons like, running away to the far side. That makes sense? It polarizes. And then we connect this to ground. Okay. If you were an electron, where would you rather be? In this object here, in this setting, or down in a 1-to-1 ratio? This is a scary environment. And it's like, oh my goodness, look at all those things. I'm out. And so electrons jump ship. Okay. And then we take away the ground And then we take away the negatively charged object, leaving this what? Positively charged, electron deficient. Does that make sense, Devin?
What if I connect ground to the other side?
Good question. If you connected ground to the other side, it's it's not definitive because it'd be attracted. The electrons would be attracted to those, but are being repelled by that. So, not much would happen. So, correct answer is C. Good with that? Okay. All right.